Alright, here we go. Oh gosh. Hello, cousin. Welcome. Uh, um, hmm. Welcome to my channel. So, I have this crazy idea that I got this book from college, okay? It is basically my book for college. For classical mechanics, the course, classical mechanics. And I have this crazy idea to pretty much answer every single problem in this book. And I will live stream it all throughout. Um, I'm not going to do it in one take. That would be Mr. Beast level, but where did my pen go? But I'm gonna try to answer them as perfectly as I can from the knowledge that I've gained from uh, back at classical mechanics course. Oh my gosh, this is gonna be a fun ride. Keep in mind, I will need. I mean, it's gonna get harder throughout this book as I progress through this book. It's gonna get harder. That's all I can say. So I will cheat. Yes, I'm going to admit that I will cheat if I am pretty much stumped. But I'm going to solve it myself as much as I can. Okay, but if I am indeed stumped, I will cheat by just looking up online and uh, or videos. Yeah, I'll do that. I'm gonna say that right off the bat. I will actually look up solutions if I am indeed stumped. Oh, hello. So do a backflip. Well, I can't do that. But explain with classical mechanics what it is first. Oh, okay. Well, it's basically physics, but from Newtonian physics to relativity, like everything that goes up to relativity. So think of everything that is physics, like general physics or anything, and goes up to relativity. There you go. And it's something physical that you can pretty much talking about the energies, the momentums of it, and that's pretty much all of classical mechanics. And you just pretty much have the systems of pretty much mechanical, right? That's pretty much the gist of this entire book. Something that is mechanical. I'm just gonna go through classical mechanics. Oh, and not only mechanical, also through rocket engineering and yeah, that like the rocket equation. And what else is there? Let's look at the topics. I'm probably missing a whole lot. You could learn about this is pretty much relativity, special relativity, oscillations, collision theory, basically momentums, and Hamiltonian mechanics. It's going to be Lagrangian equations and Hamiltonian equations, pretty much energies of systems. And what else is there? Oh, of course, oscillations, nonlinear mechanics. Oh my god, now that I look at this looks very intimidating. Oh, and of course, orbital mechanics. There it is. Like planets going around in the solar system. I'm going to be also solving that. Wow, okay. Now I know what I'm diving into right now. This is going to be. Oh boy. Alright. It's going to be a doozy. So Lagrange equations, oscillations, yeah, that's one. Energies, of course, yeah, momentums, collisions, projectile and charged particles. Oh, projectile and charged particles. Oh, that's delightful. I could do that. Well, first things first, we're just getting into classical mechanics. We're gonna go to the very first question of this book. First, pretty much Taylor 1.1. So let's get started, shall we? Taylor 1.1. Do the doozy, yeah. So let's see what happens with this journey that we're getting ourselves into. And I don't know why I'm getting myself into this. Probably just practice, but it's basically my own volition right now. And pretty much entertainment. All right, section 1.2. Wait, 1.2? Wait a minute. Oh, here it is. Yeah. I was going to say, like, section 1.2. Is there a section 1.1? If I could actually take a look at it. 1.1. I need to start from the very, very beginning. I mean, I don't want to just skip anything. So let's check. 1.1. Preface. Oh boy. Oh, this is 1.1 and there's no problems below it. Okay, no problems. Okay, good. So, oh man, this takes me back. I remember I reading this introduction back in the day. All right. Oh well. All right. Here we go. Section 1.2. Problem 1.1. Oh my. So let's see. Let's take a look. Given two vectors b equals x plus y, vector x and then plus y, and c equals x plus z, find b plus c, find b plus 2c, b dot c, and a b dot product c and b cross product c. Wow. Okay, let's do that. I'll put this aside. Here we go. Oh, by the way, the title that I have on this is like 1.1, 2, 3, and 4. I think that's what I titled this video of. I'll try to do those problems within an hour. I just approximated what kind of problems that I could do within an hour. But I think those 1.1 to 1.4 I could probably do within an hour. We'll see what happens. Alright, let's see. So I'll save this real quick. Save as. Nope, not job. Not this one. We'll go to knowledge, and then we'll go to... you know what? I'll make a new folder. Here we go. Wait, no, not 1.1. This will be called Taylor. Classical mechanics. There you go. And this would be 1, 2, 3, 4. 1, 2, 3, 4. Chapter 1 dash 1, 2, 3, 4. There you go. Better. All right. Here we go. Gotta do the thing. Oh boy. So this guy here. What the heck? Let me capture you. There you go. Let's monitor. Okay. Let me try to do this real quick. Okay. Given these two vectors, find b plus c, b by b. Okay, it's pretty short and simple. Let's just do it. So we have, I'll just call it A. Section A. 1.1. Try to find these vectors. B. No, actually, let me put this out here. B is equal to x plus c. Why am I rewriting it? Okay, let's just go to the thing. So b plus c. Here we go. X dot product plus y, and then pretty much adding this, and then you have b and then c plus z. We'll see what happens, and it looks like that this guy is just gonna pretty much add with this guy, so it's gonna have 2x that one plus y plus, oh, don't forget the hat right there, hat there, and there you go. That's pretty much it. Wow. That's pretty simple. If I am missing something, that would be super embarrassing. Alright, I'll take it. Okay, well that's pretty much the first part. You have 2x, two of these vectors going that way, one of this vector going that way, one unit of vector going to the z direction. Alright, cool. Alright, let's go for c. Here we go, b plus c. No, that's not it. 5b. 5b plus 2c. Alright. Oh my gosh. So we have 5b. B is this one. X plus y. Plus y. Pretty short and simple. And then we add it together with twice the amount of c, which is x plus c. Got it. And you will pretty much put it all together. 5x and then plus 5y plus 2x plus 2c. There you go. 5, 6, 7, 7x right there. Plus 5y plus 2z. Alright, and that's pretty much done. Nice, that's part B. Now for part C, it looks like we have B.C, dot product C. My mouth is getting dry. There's some water that spilled off my chin, damn it. Okay. Alright, C. Here we go. B dot product C. Here we go. So you have everything that is XYZ over there. Looks like I could just approximate it to just become this one. Wait, you know what? Let me lay it out first. So B dot product with C, you're gonna get X plus C. There you go. And this is pretty much saying 1, 1, 0, right? If you remember your dot products. And this one's pretty much saying 1, 0, 1. There you go. Better. Now, for dot products, you're going to end up with scalars, so I might as well just... so you're pretty much going to end up with a number. It's pretty much a scalar. So all you have is 1 times 1, you get 1, and you add it with this guy, 1 times 1, 1 times 0 now, which is pretty much 0, that's okay. And you have 0 times 1, so you have 0. Why did I put 1? Okay, so it's basically 1 there. Bam, we got it. Nice. So that's the dot product of B dot C. Dot product C. Okay. Yeah, that's good. All right. So now we have this one. Let's look at part D in this, which is basically B cross product C. Nice. And what this is essentially saying is B plus Y. Just for the sake of organization, I'm just going to put it together. And then X plus C. There you go. And the cross product in here is basically saying this, just like the same notation right here again. So 1, 1, 0, cross product, 1, 0, 1. Got it. And let's put this in a, I forgot what that notation is called, but I'll just show you. So it's pretty much I, J, K here. And then you have this guy, which is basically the one right here. 1, 1, 0. And this guy will be at the bottom. 1, 0, 1. There you go. It's basically what a cross product is, which I totally forgot what this notation is, but I'll show you the procedure anyway. So we have this guy. So at I, you're going to get this one, right? So at I, you're going to get this one. Let me, yeah. So at I, you're going to get that one. I can do this real quick. Which is basically I on the outside, and you're doing 1 times 1, which is basically 1, minus 0 times 0, which is basically 0. I'll just emphasize that there's a 0 there. That's perfect. That's the cross product. And the other one, right here, bam, bam, right there, you're going to get a minus this time. I need to recall if it's a minus. Okay, that's probably a minus. Okay, that's it. That is indeed a minus. So a minus of these two guys right here, by the way. Let me emphasize that. So we're doing a cross of this, 1 times 1, again. And minus 1 times 0, which is basically 0. I'll emphasize that. And what you're crossing with is a j, so that's perfect. Cool. And after that, by the way, feel free to correct me. It's always it's better if you correct the the teacher here if I got it wrong than telling you false information. But so far, I think it's still pretty good. Okay, so you have a cross product with, the crossing with the k here. That's perfect. And you're left with plus. It's still a plus sign, by the way. And it is going to become 1 times 0, which is basically 0. And then 1 times 1. It's basically a 1. Add it with a 1, yeah. And then this would be the k. I forgot, these are hats. There you go. And simplify this, you'll pretty much get a 1i minus 1j plus 1k. Okay, this is one notation, but since what the question has this kind of notation, I'll probably just put in x and xyz notation. So it is going to be x minus y plus z notation. There you go. And that's pretty much the end. Nice. Yeah. So that is the first question. Cool. Oh, I forgot. It's going to be... There you go. Much better. Forgot about this. All right. Any questions? No questions? Okay, good. I want to move on. So here we go. So you have General S. You got this guy. 1.2 this time. Here we go. Let's look at 1.2. Here it is. You know what? Before we move on to 1.2, I'm actually skeptical of my derivations here. So let me try to see what's happening. Whoops. Let me put over here. Let me check. You have these guys. Man, not really confident in my derivations, huh? There's a little break. Take a little break, and we'll get to 1.2. Let's see. You gotta. Let me check if this is correct. Ah. Okay, so you have that one. And that guy. What about this one? So you got 4 and minus. Does that make sense? Let me check if it makes sense. Okay. Well, this one is wrong. There's a plus there. It's supposed to be a plus. So now it makes sense. Bam, bam. Okay. There we go. That's D. Much better. Alright. Now for the dot products, it looks like everything is pretty much consistent on dot products. That's good. Got the dot products here. Yep. It seems fine. And the addition's pretty much consistent as well. Okay, good. I apologize for this. It is pretty much pluses over there, just to keep in mind. All right. Now, moving on. 1.2. Here we go. Nice. 1.2. Two vectors are given as b is equal to 1, 2, 3, 3, 2, 1, c, 3, 2, 1. Remember that these statements are just a okay, yeah, I get it. Find b plus c, 5b minus, okay, etc. Yeah, all right. Let me just do it real quick. So a is equal to this one. Where are you? B plus c. Yeah, b plus c. B is 1, 2, 3 plus of c is 3, 2, 1. Cool. And we're pretty much adding them one to one, you know? This is pretty much it. Okay, so I'll put it right here. Green one over here. Oh wait, that looks ugly. And put a green one over there. And then yeah, like that. There's multiplier over there. Okay, so this guy is multiplied. Wait, applied? No, added onto 3. 1 plus 3, which is basically 4. And then 2 plus 2 is basically 4. And then, oh, they're all 4. 3 plus 3 is equal to 4. Okay, good. Alright, nice. You just pretty much added these vectors together. And this is the final result. Cool. Short and simple. Now for part B, however, we have 5b minus 2c, and pretty much doing the same thing. 1, 2, 3 times 5 plus 2 times 3, 2, 1. Nice. And now we have, let me check here. Okay, got it. 1 plus 2 times 3, 2, 1. And this is going to be 5, 10, and then 5, 10, 15, 15. Plus 6, 4, 2. And pretty much doing the same thing right here. So 5 plus 6. 5 plus 6. 10 plus 4. Still looks ugly, but got this side. 15, 16, 17, yeah. Okay, 5 plus 6. What is it? 11. And this would be 14. And this would be 17. And that's your final answer. Nice. Short and simple. Moving on. B dot product C. Here we go. B, C. B dot product C. Ouch. That actually hurt. Okay. B dot product C. We have this guy. It's going to become 1, 2, 3. Cool. We expect it to be a scalar. And then 3, 2, 1. Perfect. And we're going to do this guy. 3 times 1 is equal to 3. Added with 2 times 2 is basically 4. 3 times 1, 3. And 4. 5, 6, 10. Yeah. 4, 5, 6, 7, 8, 9, 10. Yeah, 10. Okay, good. So that's a 10. There we go. Now for the last part, B cross product C. Here we go. B cross product C. Nice. So we have 1, 2, 3. Cross product with 3, 2, 1. Short and simple. And we pretty much do the same thing that we did up here. This thingamajig. So we're gonna get I, J, and K. 1, 2, 3 first. 1, 2, 3. And then 3, 2, 1 over there. 3, 2, 1. And you're left with this guy. What do I need here? Nope, that's not it. Good. So this guy is going to be left with, I'll do the i's first. So this guy will be equal to some I. 2 times 1, right here. 2 minus 2 times 3, 6. Perfect. And then you're adding, not subtracting, adding. You're adding with this one right here. So, oh, forgot. I need to make a J here. Better. Bam, bam. And then this would become white, and then J. Good. So we're doing the same thing. 1 times 1, 1 minus 3 times 3, 9. Cool. Next one. So we have the IJK. Now we're doing the thingamajiggies over here. Yeah, K, the K one. We're doing the K. So it's going to become the K right there. 1 times 2, 2 minus 3 times 2, 6. Everything seems to be consistent. Good, good. And we're just left with this, -4. I gotta keep doing the hat here. Plus 1 minus 9, -8. J. Plus 2 minus 6, 6 by 4. Whoopsie, -4. And it's gonna be a K. And lo and behold, we're pretty much left with -4, -8, and -4. Cool. Final. All right. -4, -8, -4. It's going to be the last one. B cross product C. All right. We pretty much got 1.4 now. Wait, 1.4? I meant 1.2. Yeah, that one. 1.2. Good. Let me check if I have everything here consistently. Taking a little break. Okay. Nice. All right, here we go. So we don't need these. These, and we need Taylor here. Taylor, got it. All right, here we go. Moving on, 1.3. Oh boy. Control S. Ooh, okay, this is some proofing problem. Get this over with. Control V. Wait, what? Oh, it's not letting me do it. Oh, that's strange. Oh, okay, it's not letting me do it. Here we go, let's do it again. 1.3. Control V. As monitor. Here we go. All right. By applying Pythagorean theorem, the usual two-dimensional version, twice over, prove that the length r of three-dimensional vector r equals xyz satisfies r squared equals x squared plus y squared plus z squared. Oh, interesting. Okay. Let's see what happens. Where do I start off with this? Applying Pythagoras theorem. Usual two-dimensional version. Twice over. Prove that the length r of a three-dimensional vector r satisfies r squared equals. Let me think. What would be a probable solution for this? By applying Pythagorean theorem twice over, prove that the length r of a three-dimensional vector. Okay, well, let's try to visualize this first. So we have this guy, going that way, going this way. I'll do it like this. This way and going that way. There you go. This will be Y, X, and then Z. Got it. And our vector will be in the middle right here. Not on the Y x-axis, just so you know. It's gonna be pointing along the side right here. It's a triangle right here. There we go. And there's gonna be a right angle right there. That looks three-dimensional. You know what? Let's make it more three-dimensional. There you go. Yeah, whatever. No, I'm not doing that. Don't worry about that. Okay. So we have something like this, where there is an X component right here, and a Z component over here. And then there's going to become, what am I missing? Oh, of course, Y component. Here it is, right here. So Y component right over here. Nice. Oh, and this is also a right angle. Actually, I'll put it over here. Also a right angle. No, I'll put it right here. Right angle. Also a right angle. There you go. Better. It's also a right angle. Nice. Okay. What am I missing? So this would be the R. It's better. Okay. What's next? Apply Pythagorean theorem. Prove that the length R of 3 dimensions vector satisfies that guy. Alright, I'll just keep that in mind. Prove R squared is equal to x squared plus y squared plus z squared. Good. So let me try to solve this by myself. Let me check. So, I mean, doing the original Pythagorean theorem, we could actually figure out what this is, right? Actually, we could figure out what this is right here. Yeah, this triangle right here. I'll make it magenta, make it easier for us. This triangle, we can figure out what this is. Right there. We could do that. So if we figure out that triangle, let us just make that looks ugly. Hold up. Let me do this real quick. Like that. I'll take it. And this is a right angle. Yeah, let's do that. So this would become the Z. I'll call it Z naught. Just to assign it. And then X naught. Good. And we're pretty much finding this guy right here with the Pythagorean theorem, right? So this side is basically x naught squared plus z naught squared. I'll call this, what do I call this? I don't know what to call this. L? I'll call this L. Pop up. Whoop. L is equal to L squared is equal to x naught squared plus, oh, that's a z. Yeah, z naught squared. Got it. I'll do it like that. Better. And then from that, we'll call this the y naught right here. That's good. And this y naught over here was going to be a combination of this line and this line to make this hypotenuse, because r is the hypotenuse in this case, right? So therefore, I'll just say line L is equal to, wait, I'll say it in the proper terms right here. There is a triangle on plane, I'll say on xz plane, on xz plane. There's a triangle in xz plane, and xz plane. I'll say with legs, yeah, legs x naught and z naught. I think I'll be more specific here. There is a right triangle. Better. Right triangle. Better. The xz plane with legs x naught and z naught. The hypotenuse L is equal to I'll call it like L squared. Sure. I'll do L squared. Hypotenuse L squared is x naught squared plus z naught squared. That's better. Hypotenuse is equal to, yeah, that thing. Good. All right. Now let's see. There will be some sort of, yeah, the L is now the leg of this right triangle. This guy. L is now a leg. I don't know what plane this is, by the way. What plane is this? It's gonna become in between. How would I explain this? The L is, that's a giant state. There we go. The L is a leg of right triangle tangent, I'll say tangent, tangent to the xz plane. With another leg z, wait, what am I missing? Y naught, yeah, that one. Y naught, good. That looks better. The hypotenuse is now hypotenuse is r squared is equal to L squared plus y squared. And you know what L squared is basically these guys, and lo and behold, hence r squared is equal to x squared plus y squared plus z squared. I think this is a QED, guys. There we go. This is a QED. I'll just say layer. Hence this guy, and then QED or box, whichever you like. Nice. That's a cool little proof. 1.3. Cool. Nice, nice. All right, moving on to 1.4. I think we could make it to 1.5 eventually, but one of the many. Oh wait, I'll just put it here. 1.4. Forgot about this. All right. Control V. Nice monitor. I think I should. Should I put music in this? Streams? I'm not sure. We'll see what happens. All right, 1.4. Here we go. One of the many uses of scalar products is to find the angle between two given vectors. Find the angle between the vector B and C by evaluating their scalar product. Ooh. So the dot product, huh? Okay, interesting. I remember one time that there's gonna be like okay, so here's pretty much how you do it. If I remember correctly, actually I do remember correctly, that the dot product of this B dot C is basically the length of B multiplied by the length of C times cosine theta. And the theta is actually the angle. And then putting it all together, you got B dot C over the length of B, the length of C is equal to cosine theta. And you pretty much manipulate this to create the arc cosine theta. That's pretty much it. And you pretty much solve it. I don't even need to do it. You got it. Sorry about that. I've been talking for the past hour. Okay. But for the sake of it, yeah, I'll just do it. Whatever. Here we go. So first, find the B dot product C. Here we go. 1, 2, 4. 4, 2, 1. Why is it always like the reverse of it? Like between B and C. Oh well. Okay, so we have the same thing. 1 times 4 is basically 4. 2 times 2 is basically 4. 4 to, okay, now you're just getting ridiculous. 4, and this is going to become 4, 8, 9, 10, 11, 12. Good, got it. Now the length of vector B is basically doing the Pythagorean theorem of these parts. So you have square root of 1, 2, 4. Square root of 1, 2, 4. 1 squared plus 2 squared plus 4 squared. There you go. Ow. And then we have this guy. Oh, whoops. 1 plus 4 plus 16 square rooted. 16, 17, 18, 19, 20, 21. Ooh, interesting. And it looks like C is the same thing because it has the same components, 4, 2, 1, right? So it is basically 21. Square root of 21. Okay, so let's put it all together. We have, I'll put in green here. We have this guy, and this guy. Put it all in here. And we have 12 over square root of 21, square root of 21, etc. 12 over 21. Nice. And this equates to cosine theta. And you're pretty much putting it all together. Arc cosine of 12 over 21. Oh wait, you can simplify that, huh? Hold up, let me see. It's gonna be 4 over 7. It's like 3, yeah, makes sense. 4 over 7. Dang. Okay, so 4 over 7 is equal to theta. Got it. So let's put this on Desmos. Here we go. Where's the Desmos? They were. English on Desmos. 4 over 7. Our cos of 4 over 7 is equal to 0.96 radians. Okay, that's fine. 0.96 radians. Not even a pi. Dang. 96 radians. That's a pretty small angle. Let's put this in, I forgot what it's called. Degrees. Yeah, degrees form. There we go. So we have, well, so we have this guy. 180 divided by pi 55. Oh, well, I was wrong. It's a pretty large angle. 55 degrees. There you go. That'll be more intuitive. 55 degrees. 55.2. That's fine. Degrees. Got it. And that's the final answer. 1.4. All right. 1.4. We got it. Can we do another one? Not sure. Yeah, we can. Okay, let's try to do another one. Here we go. 1.5. Nice. Let me see if I could do this real quick. There we go, 1.5. This monitor, good. All right, so 1.5. Find the angle between body diagonal of a cube, any one of its face diagonals. Body diagonal of a cube, and any one of its face diagonals. Okay. Hint, choose a cube with side 1 and with one corner at O and the opposite corner at point 1, 1, 1. Write down the vectors that represent a body diagonal and another that represents a face diagonal. And then find the angle between them as in problem 1.4. Okay, I see. It's pretty much the same thing, but doing that. Okay, now it makes sense. So you're trying to draw a cube on the x and y coordinates, and z actually, x, y, z coordinates. We'll do that. Let me try to put this over here. Got it. Okay, x, y, and z coordinates. We'll do it again. Bam. Bam is going to be a cube, so I'll put it over here. 1, 1, 1, 1, 1, 1. Cool. And it looks like, find the angle between the body of diagonal. Let's visualize this real quick. So this is the face of this one. Oh, I forgot. Y, X, Z. Cool. And then we got this guy is going to be another face. I'll make him different colors. So this is going to be the second face right here. Third, I mean. The third face. Cool. And then, okay, this is going to look silly. But, this will do, actually. Here we go. Got the face. This looks very ugly. I'll take it. And there's going to be, like, another face right here. There you go. Ew. Gross. But this is the one that we're actually trying to find. It's this angle. I'll put it in white. This guy. Should I put it in white? I'm not even sure. You know what? Do I even need to color the faces? I'm not going to color the faces. I'm going to make them all white. It's better if I just do it that way. It's better if I just do that. Okay, here we go. So I'll make them white here. Good. Good. Alright, that's a better visualization. So let's go by the hint. Choose a cube with side 1 and with one corner at O. Okay, so this is the O, origin. And the opposite corner at point 1, 1, 1, which is basically this guy. Got it. Write down the vector that represents a body diagonal and another that represents a face diagonal, and then find the angle between them as problem 1.4. Got it. So we will deduce this side right here. Up, 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 up. Actually, would it be better visualization if I do this? Like that. From this corner to here. And then you're going from this corner from 0, 0, 0 to 1, 1, 1, like that. So it's from there. Just like that. Vector here and a vector here. And you're trying to find these two things. This is the angle that you're trying to find. This guy. Shoo, boop, boop. Theta. Got it. So that's a good visual of it. So this vector right here, the green one, is actually gonna become X. Wait, no, that's not X. Y, x, z. So this green one is actually vector 1, 1, 1. Okay, I'll put it in green. 1, 1, 1. And then vector of the purple one is basically 1, 0, 1. Yeah, that's it. 1, 0, 1. Cool. 1, 0, 1. So what this question is basically saying, in other words, find angle between 101 and 101. There you go. And we're pretty much doing the same thing as what we did in 1.4. This guy. And then manipulate to this, yeah, etc., etc. You get the idea. So we're pretty much putting it together. 1, 1, 1. Dot product 1, 0, 1 over 1, 1, 1. 1, 0, 1. Is equal to cosine theta. And we pretty much do the same thing. Numerator, it's going to be 1 plus 1. Wait, no. 1 plus 0. 1 times 1 is 1. 1 plus 0 right here. 1 times 0 is 0. 1 times 1 is 1. Plus 1. Got it. The 1 on the bottom is basically 1 squared plus 1 squared plus 1 squared. And then, oh, whoops, that's a multiplication. Multiplied by 1 squared plus 0 squared plus 1 squared. And it's pretty much 2 over 1, 2, 3, square root of 3. And that will be 2. And looks like this is going to become a cosine theta. And this is going to be 6, square root of 6. It's equal to cosine theta. And you're pretty much doing the same thing. Your arc, cosine 2 over square root of 6. Cool. Is equal to theta. Oh my gosh. We pretty much have it right now. Let's put it on Desmos. So arc cos of 2 over square root of 6, 0.61. Okay. Nice, nice. It's going to be lower than this guy. Oh, where is it? There we are. 0.615. 62. 0.62. 0.62 radians, rad. Or I'll just do it in degrees right now. 180 divided by pi, 35 degrees, 35.3. Same thing. And that's pretty much it. Wow. It's 35.3 degrees. Wow. So far so good. We went through 1.1 to 1.5. Looking forward for it to be more difficult than usual. So this pretty much concludes our first few problems of this book. And I'm getting really tired, so I might as well just go to sleep right now. Alright, I'll see you guys next time. This would be a very huge journey for me to finish this book. I'll make time on streaming. I'll try to stream every day. Let's see what happens if I stream every day. That'll be fun. Till then, oh, forgot to save. Don't forget to save. There you go. All right. See you guys next time. Oh, and happy learning. Yeah.